Okay, welcome to the fourth quarterly webinar of the Black in Mathematics Association. Today is a very special one because we have a training on Epiverse-TRACE for modeling diseases, and disease analytics and all of that. And I know that you are here for a very great time. For everyone who has been here all along, thank you so much. And as we kick off now, I like to, okay, I mean, we don't have too many people, so I can still go over the names. There's Amancado. If I got that right, there's Amancado Ako. Okay, I couldn't get the full name. Then there is Amar Bishal. Thanks for being here. There is Bernard Asamoah Aful. Thank you so much for coming. Eman Madi, that was the first person to come in like 6 minutes before we started. And Dr. Idisi K is a member of BMA. Then we have Oluwafemi Samson Olagbami, also a member of BMA. Thank you all for being here. So like I said already, we are here to talk about, to have, in fact, a hands-on session, by the way, on Epiverse-TRACE for disease analytics and modeling. So what I'm going to do is, we have two speakers, and they are Andree Valle Campos and Dr. Abdoelnaser Degoot. So I have their citation. I'll quickly read, and then I'll see the floor to them, so that we don't take too much time, so that we can have enough time for the training. Okay. Sorry, just a minute. I'm trying to pull this up now. Okay. Yeah, so I start with Andree Valle Campos, who works at the London School of okay, I guess I have to face the camera. So Andree Valle Campos works at the London School of Hygiene and Tropical Medicine, LSHTM, on the Epiverse-TRACE project, providing interoperable R packages for outbreak analytics. Andree develops training materials and has co-led international workshops and online courses. Previously, Andree collaborated with the University of Geneva's Graph Network and CDC Peru, and studied at Universidad Peruana Cayetano Heredia, UPCH, and Universidad Nacional Mayor de San Marcos. So welcome, Andree Valle Campos. And then I move on to Dr. Abdoelnaser Degoot, who is a research fellow in outbreak analytics at the MRC unit, the Gambia, part of the London School of Hygiene and Tropical Medicine, LSHTM. He earned his PhD in applied mathematics from the University of KwaZulu-Natal, South Africa. He contributes to the Epiverse-TRACE project by testing R packages developed by research software engineers, RSEs, creating use cases, co-developing teaching materials, organizing and teaching workshops, and supporting adoption efforts. So please make welcome Dr. Abdoelnaser Degoot. Don't forget, our topic for today, what we are considering today, is Epiverse-TRACE, and so outbreak analytics and applied infectious disease modeling. All right, so at this point, I see the floor to our trainers. Thanks a lot for the privilege to have you here.
Nice. Thank you very much, Emmanuel. I think that I'm going to start sharing then my screen. Just a sec. Can you please confirm me that you are looking at my whole slide deck?
Yes, it's on.
Yes.
Yeah.
Nice. Okay. Nice. So thank you very much for the invitation to the association and all the colleagues that approach us to this network. So today we're going to talk about, as you can read in slides, Epiverse-TRACE, outbreak analytics, and applied infectious disease modeling using R. So our plan for today, I'm going to start first with a brief introduction of what's the Epiverse, what gap we're filling, and then Dr. Degoot will provide us an introduction and a demonstration on how to simulate interventions in an SEIR-B model using epidemics and other packages in that process. And at the end, we plan to have like an open session for questions or a space for questions. So without further ado, I will start with this first part of the presentation. And I would like to start talking about a blog post done by Dr. Adam Kucharski that is about, as you can read in the title, how well prepared are we to rapidly analyze a new influenza pandemic? A brief perspective on analysis conducted for UK government advisory groups during COVID-19. So this blog post aimed to assess this question. If another pandemic were to arise, how easily and quickly could we repeat this analysis? So a lot of analysis were done during the COVID-19 emergency by a lot of colleagues. But what about the next one? So about the code availability, is the original analysis code public or it is not? About the package availability, is the analysis code or underlying method currently packaged up for quick reuse? And the third criteria was on task readiness time. How long it take to get the code or package in a rough state where it could be rerun an equivalent analysis using the characteristics of a future transmissible influenza or any other disease. We can expand this to any other outbreak or a potential epidemic in each of our countries. So based on code availability, how it is packaged, is available as a package, and how quickly we can reuse it were three of the criteria that were used for this assessment. So four of the tasks that were um, assessed in this blog post include early estimation of transmissibility, the probability to control an outbreak, or the probability of having an outbreak that we would have more challenges to control. The second one was on early estimation of severity. What methods are we using to account for biases related with an early estimation of severity, accounting for all the biases that these imply at the early stage of an epidemic. The third one was on early population level scenarios. That is kindly related with the example that Degoot will guide us today later. But how much time it will take us to provide an answer for population level scenarios. And a third one that is quite related with the transmissibility of a disease is the analysis of super spreading. Are we having super spreading events? What evidence should we, or what type of data we can use to analyze for this? So here I have a question for all people here that is present at this moment. Just to take 1 or 2 minutes, just or possibly less than a minute, how much time giving answer to this task would take you to how much time it would take you to solve this task. Just quickly reflect about this and try to give you a sense of how much time. Imagine that you are in a scenario and that you are well placed to provide answers because you have the technical capacity, you have the training, you have the interest, you have the tools. But how much time it would take you to provide answer to this? Like a couple of minutes, hours, days, possibly within a week, to collect all the required information, all the parameters. Please, if you have, I don't have access to a chat here, but if you can reply on a chat, it would be nice. If not, you feel free only to write down in a piece of paper how much time it would take you. In the meantime, we ask these questions to different groups, to a group of like a selected group of experts in a certain country, and some of them were replying like, we record like a full day to have all of these tasks done, not asking them by exactly what they would do, but possibly within a day and a half. If they, for example, reuse their own piece of code that they used in the past, possibly they only require like half a day, but possibly accessing to all the parameters require accessing to the literature and going back to different pieces of information. So I just want to move on. So I hope you think a little bit about this. If you don't have any assessment on how to solve this, no worries. We're going to show you what we have for you and how we're covering this gap. So in the assessment, based on the recent efforts that we did with the Epiverse-TRACE initiative, by building our packages, we managed actually to solve these three, or not solve, but try to reduce the gap between the requirement and the possibility to reuse in a quick and easy way these type of estimates. For example, we now have packages like super spreading or RP chains to estimate the probability to have an explosive outbreak at the early stage of the epidemic. Like we can only take like possibly, as it is estimated, there are like possibly days to have a rough estimate of this. In the case of severity, we now have the CFR package that we have code available, package available, and we can solve this like within hours, and to have robust estimates in a couple of days. In the case of early population level scenarios, we now have a package that is called Epidemics that again fulfills the criteria of having code available. The methods are already packaged in, as I mentioned, in Epidemics, and we can have this in roughly hours, or we can take like some hours to have a rough estimate of the task that we want to solve. And about super spreading, we didn't have code available, but now we have like the methods embedded in a package, and we can take a couple of minutes just to have a robust estimate of the implications of super spreading from contact tracing data, for example. You can find this estimate in this link. I think that after I finalize, I'm going to share like a set of links of these, but if you are like kind of urgent, you can go through the links that are going to be at the end of my slide. Okay, so just moving on, the set of packages that I'm showing you at this slide is a set of packages of general tasks, general questions or frequent questions that we prioritize in the analysis. While there are other questions that possibly require more time, are more specific to the context, like for example, transmission dynamics of variants, that we may not have packages, but we can rely on code repositories available on GitHub. That is also part of the practices that we wanted to disseminate. Okay, all of this introduction is because I want you to share with you the approach that we took and that triggered Epiverse. So in this type of assessments, from the start of the project, we asked to different colleagues in the community, to different experts, and one of the lessons that we learned is that we have the opportunity to diagnose or to identify what are the most predictable tasks. Predictable in the sense that a lot of people will need to solve them, and that we for sure will need to give an answer for that at the early stage of an epidemic or an outbreak. So in the green, just to highlight with the laser. So in the green circle here that we have, we're targeting, or we targeted, or we found like an opportunity to proactively develop general tools that for sure most of people will try to do. But by providing tools for these highly predictable tasks, we can free up time for these type of problems that require tailored approach and domain knowledge. Tasks that we possibly will not be completely sure but are highly dependent on the context of the disease, of the specific expertise for that type of situations, and possibly it's going to be more specific for different geographies. So this is the main task that we try to cover, how to provide tools to accelerate our response and reusability of efforts from the past. Not only from the colleagues that were part of this project, but also from other code available online. So at the start of the project, we started with identifying the questions. We, if you access to this blog post linked below, we had a workshop and we asked for how the first 100 lines of code would look like at the start of an epidemic. So we talk about creating a scenario modeling. What could be the final size, the total attack rate of an epidemic, accounting for heterogeneity in the population, accounting for heterogeneity in the susceptibility in different age groups, or accounting for heterogeneity in the contact between age groups. We know that we need to deal for that when assessing different scenarios. Or how many infections could be averted by overlapping or sequential interventions. We can plan different set of interventions in different ways, but giving configuration to all of these require time, and how flexible we are to test hypotheses of overlapping or sequential interventions will be crucial at the early stage of the epidemic. Then, of course, we needed information from the real time of the assessment that could provide us key inputs for building up these scenarios. For example, the question of how many people are getting sick weekly, the transmissibility of the disease, how many people is experiencing death, how severe is if the disease that we are observing, and are we observing super spreading? What implications that have on the scenarios that we were planning, as we mentioned briefly. And of course, if we are getting estimates in real time, we need to rely on data that we're collecting at this early stage. So we ask about how to clean and standardize data, how to protect against changes in the data. If anyone was in the moments of the COVID, possibly we had like a lot of different changes in the input data that had implications in our data workflows, and what patterns of disease of a spread we're observing. Just describe the patterns between different categories in an outbreak. So we relabel these three different tasks by early task, middle task, and late task, because between all of these questions, there are inputs and intermediate outputs that communicate all of these tasks to fulfill all of these assessment of the outbreak at the early stage. So our response or our effort or the work, specific work that the team of research software engineers has introduced in one of the introductions was building software. So we packaged up some methods that help us to cover different aspects and different questions between this gradient of early, middle, and late task. So we have a lot here today. Possibly we're going to talk just about 3 or 4 packages, but these are the main products. So from reading, cleaning data, and etc. I'm just going to guide you through. Something to speak about the software is that we provided, or we had the benefit of time of working a lot on the documentation. And these software are not only isolated pieces of code in different package repositories, but we also try to inspire in a documentation system that is called diataxis. You can also find this reference, and I will share this later. So this diataxis framework divide documentation of software in these 4 different, let's say as a coordinate system, these four different, um, you will understand what I'm saying. So for example, if you want to learn, if you want to study during, let's say, these peace times, you can rely either on blogs or vignettes to learn, for example, how the package was built, what challenges, what blockers we find, and how we are integrating the community in different efforts. You can also, if you feel that you need to learn from scratch, from the beginning, you just learn R and you also learn how to build infectious disease models, but you want to learn about this tool set and also learn about new concepts in the middle, you can rely on tutorials. You can rely on tutorials which will not have material for study and covering theory, but you will access some practical content. You will have challenges, you will have some explanations, and some redirection to complementary learning materials in your practice. But imagine that we are now in response time. Let's focus at the right side of this graph. We need to use this package as these packages actually to work because we need to respond to an emergency. So you can be familiar to some practical guides. For example, these are the how-to guides. The how-to guides are like recipe-like entries when you, if you are like quite competent practitioner or already experienced on the things and you know what you are targeting, you can go to these recipes as similar as you already know what plate you would like to cook. You only need the recipe just to remember all the steps because you already know how to get this and you already know what are some of the more challenging concepts or more, let's say, some of these guides have concepts that I even don't recognize fully, but there are some experts, colleagues that manage to provide some of their entries there. And as always, you possibly will refer not to the tutorials to go back to different chunk of pieces, but you can go directly to reference manuals that will have a specific information about all the arguments for the functions. So this is called material. This reference manual is called material that will not going to teach you and give you details or context, but will help you refresh your memory at the response time. So apart from as I mentioned, we have this component of studying, of teaching, of building capacity or capacity building, and we provided a set of tutorials. So we divided also our tutorials in these three sections. And I just going to briefly open you, for example, that in the early task tutorials, we teach you how to, or you can learn how to read, clean data, aggregate, and visualize using a set of packages, a subset of packages of the ones that I showed you before. Not only packages that we build, but also built by other initiatives in the ecosystem that we are also embedding in these trainings because we aim to connect the current ecosystem. We have a set of middle tasks, as I listed before, transmissibility, severity, forecasting. And for this, we are connecting this first set of packages that are highly dependent on what you learn on early tasks to provide answer to this task. We have another set for account for super spreading or transmission chains. And again, we are connecting packages that already exist, like Epic Contacts and Fit Distribution Plus, that are possibly Fit Distribution Plus is more generic, but we are also recruiting Fit Distribution Plus to connect that with super spreading and Epic Chains packages. And lastly, some of the topics that you will also see later will connect these three different sections in some way that is about scenario modeling, modeling interventions, and comparing public health interventions with packages like Social Mixer and Epidemics. So, well, during these trainings, I mean, these are not isolated episodes, not isolated packages, but we try to cover what we mentioned at the beginning, the predictable task. So, in order to facilitate the identification of tasks and to get like more predictable pipelines, we are connecting through these tutorials all of different components because we know that there are some input output dependency between each of these. So we can follow, as today, we're going to import line list data. We're going to secure that we have this in incidence format to estimate the reproduction number thanks to accessing to delay distributions. And then we're going to simulate interventions by accessing social contact surveys, demography information, and also intervention data. But you can also follow other paths, like for estimating the upstream distribution and any downstream analysis. And this is not closed entry. These are like tools and entries that are also open for any other downstream task or upstream task that you find it appropriate. We'll get back to this plot later if you want to look this at more detail. So apart from having the software and the training and providing this pipeline for outbreak analytics, we also are trying to get some kind of integration. We just finalized last week a training that we did for the Africa region, for the Anglo-speaking countries or English-speaking countries and French-speaking countries, providing some multilinguality to our training materials in an effort to connect between different institutions that are quite familiar in the ecosystem, like Applied Epi. They provided an introduction to field epidemiologists in different countries. Then they were trained by the Epitech initiative that is based at Javeriana University, that they led this set of 4 different topics team to introduce into data science for public health and some concepts in modeling. And then we took the next step on outbreak analytics and applied modeling, which is the work that Dr. Degoot and myself work together to try to disseminate these trainings in different countries. One minor comment would be that we also thought on learner personas. We try to focus on or try to adapt to our audience that were specifically field epidemiologists. And we also like drafted potential learning journeys for all of these profiles, because all of these pieces of material could serve differently for different audiences. Whether you are a researcher, possibly you can go to more to next step task like model fitting and inference from modeling and other tasks that would expand your learning. But if you need to recall from more practical tools, you can also go back to this previous training. So we have different paths for different audiences, from field epidemiologists, analysts, on PhD students doing research. We're almost finalizing this introduction. So as we talk about the software, we talk about the training component, but we could not do all of this without the community or the range of network of different colleagues and organization institutions that are providing um, relevant inputs for this initiative. Everything started, let's say, with this core group powered by data.org, with people at the London School, Javeriana University, and Los Andes in Colombia, and the MRC unit at the Gambia. But then we expanded also our contact with WHO, the Epicenter, Imperial College, Recon, Epiforecast. There are many different organizations, and also the Ministry of Health of the Gambia and Hong Kong University that help us to expand the reach of all of this effort that we did in the last 3 years. And lastly, we don't have like a closed community. We're open for different levels of collaboration and different levels of involvement. We have like different experiences, for example, of people standardizing tools or adhering to some of their initiatives to provide some interoperability with Epiverse. I mean, interoperability in the sense of making our efforts intercommunicated so that we can connect the outputs of a different package to the inputs of any of the efforts that we were building in the pipelines. So here we based on the WHO collaboratory initiative. Then, for example, we have also examples of integration, incorporation of tools to Epiverse pipelines. In this case, we have a really nice example that we start building a package to access to parameters, access to the incubation period, access to the serial interval, access to generation times, access to different parameters that are useful for real-time and scenario modeling. But we also have other colleagues elsewhere, like that were doing efforts for doing systematic reviews of parameters for different disease, different outbreaks in the past. When we don't have the parameters for an outbreak in the present, we can rely on historical parameters of historical outbreaks. And this work was done by an initiative called BERG. They were building an epi review packages, and we work how to integrate these two efforts smooth to provide like a smoother experience to the learner. And lastly, the closest level of involvement could be co-development of tools hosted by the Epiverse, like the topics of participation. And here you will, if you are in touch with this topic of social contact matrix, you will see that things will change in the coming months, really, because possibly we'll have a new package that will help us to integrate the different efforts of colleagues building the social mixer package and also the Kongmat package, that now they found that there are some pieces that could be that could work a little bit nicer if we integrate efforts and co-develop a standard tool good for a wider community of users. So that's it. I think that we have here a brief summary. Epiverse-TRACE, if you ask about what Epiverse-TRACE was, it was the universe of epidemiological something. Epiverse-TRACE is software, a set of R packages that are also complemented with a documentation system involving a piece of training aiming to scale up or to increase your expand the tool set for field epidemiologists, researchers, analysts in general, based in trying to create a community of practice of developers, users, and also building different levels of collaboration throughout this path. So that's it. I think that we are almost ready to move on to a next stage, and possibly before giving hand to the good, we can start by sharing you. This is going to be a brief step before moving to the live coding section. Is that we're going to use an Epiverse, a Posit Cloud session, and possibly we can take time to make sure that you have access to this Posit Cloud, because this requires possibly a little bit of not setup, but just just making sure that you have access to this and that you create a copy in a session. This will require you to create a session in Posit Cloud. Hello, someone is there, I think. I don't know who would like to talk.
Andree, I just paste the link in the chat so they can use the link of
Nice.
the servers.
Nice.
Yes,
Thank you very
so
much.
so the post the QR code or the link takes us to the same place, I think.
Yeah.
Yes,
Yeah.
same place. Yes.
All right. Thank you.
But it possibly something may happen with a QR code. It's not to use on your cell phone, so if you would like to work on your computer, please better use the link.
Yeah, the link is
It's
easier.
yeah. So I just want to move you through two more slides before moving on, that will show you possibly if you already access to the link, possibly you have this platform that will require you to create a session. Feel free to log in with GitHub or Google, or just create a new session with your email. We are going to have like the time of the good presentation. If you have any issue related with this, you can have this time. We're not going to start right now. We're going to first hear to the good. So after you move on of this step of accessing to or logging in with a session, you will have this type of depiction. You will have like an access to a POSIT cloud. You may need to wait a couple of seconds before the project is fully deployed. And make sure to create a local copy, because you will have this message of a temporary copy in the upper, in the header of the website. So you can kindly save a permanent copy. And then you will have a local copy, not local copy, but a permanent copy for you in your session of POSIT Cloud. So you possibly may need to take a couple of minutes on that, or possibly a couple of seconds, but make sure to create a local copy and save a permanent copy for this. That said, I think that the good I can let this to you, whether you want to proceed with directly or proceed differently.
Yeah, I think we have like we have some minutes. Let me just finish the theory part and then we take a 5-minute
Nice.
break and then we start the demo.
For sure.
Okay, so I continue from where Andree has just stopped, but by the way, the official acronym for TRACE is Tool for Response, Analyze, and Control of Epidemic. Good. So, what I'm gonna do is we want to do a short demo, to show how easily one can use our tools, and I target just scenario modeling, assuming that most of you are coming from mathematical background and understand mathematical modeling. So that's my task. But let's now have a recap of the mathematical modeling and then what the scenario modeling. So scenario model, why we do need scenario modeling? Scenario modeling is done on a population level. You want to see the trajectory of a disease, what it look like. This is the default case if you don't have any interventions and that. But if you want to assess certain certain interventions that has been in place, or if you want to make an informed decision, and if you want to see what the best possible potential of that trajectory of the disease community, you need the mathematical modeling. Then you impose intervention and see what is a good one. So this is and what you are looking for is you might impose more than one scenario. Okay, you can assess multiple scenarios, maybe in a sequential way, maybe in an overlapping way. Okay, that's the scenario model is done on the population level, and the theory of mathematical is you can develop your own compartmental model or stochastic model. You have the math, but how to analyze that effectively in a short time and in a standard way. That's what epidemic bucket does. So, and it can be a heterogeneous population if you have a H structure, okay, as shown in this curve. So here example of when you close the schools, okay, the curve might come down, okay. When if you close the workplaces also, it drastically reducing down, and when you lift up those at a certain moment, the trajectory go up and down. So that's the kind of what if scenario modeling, and it's very important to make informed decision and also plan for intervention and allocate your resources. And in general, so we are looking at the peak of the infection. Okay, people want to go, policymakers, okay, they want to go to the peak as low as possible. okay, so that their health system can accommodate the sickness, the sick people, or they don't want to overwhelm their health system by a lot of infections. And the other important point is also the time. Okay, you want to reach peak at certain time. Okay, which is also important, and the size of the peak. So those are the two indicator, or maybe three indicators. Okay, peak infection, the size, the location. These are the indicator to tell you whether you can okay, your health system is effectively can address the response to the outbreak and epidemic. And for this, so that's what epidemic is. We are not developing a new model. We are just reusing or make this simulation modeling is easier. So what you do, you can create a lot of intervention, also compare, okay, how many number of infection in each scenario you averted, okay, as a new infection, as in the second graph here. You can compute what if I just if you impose a mask, okay, mandate. What if you close the schools? If you would close the workspace, how many? Okay, one. What will happen if you do okay multiple interventions at the same time, and how many people that you then you choose what's appropriate intervention according to your situation. That's what the policymakers they just need for figures and numbers. How to so epidemic is facilitating to do that, okay, and it's a library of composable models. Composable in a way that in each model we have a population. Okay, we have our model object, which it take the population object. That population object is whatever model we need that population object, which you specify your demography vector, how many people you have in your population, and then if you account for heterogeneity, then you need a contact matrix. If you have a, for example, if you have a group, okay, or any other group, then you need how those people are interacting, okay, and you need the initial conditions. That's the basics, okay, of the mathematical model of infectious diseases. This is something common, and you can develop your own whatever model you like it, and most of them are maturing, okay, they are well studied like SIRB, so they are suited for many diseases, and this something has been done, okay. And then after that, in order to run your model, you need a parameter, okay, epidemiological parameters, okay, like the transmissibility, infectiousness rate, recovery rate, and other parameters that govern your system. So you run it. This is standard, but epidemic now breaking things into components, so become composable. And then optionally, here is what value of epidemic come. You can impose interventions. Okay, that intervention then alter the trajectory of the disease. So intervention, they are separate component. You can add it. And of course, I will talk about the type of intervention, but it's also they are taking certain features. How, in what window you want to interval, you want to place the interval, and what that interval intervention does. Is it changing the social contact, that reducing the contact, or it's reducing it's changing some epidemiological parameters? Okay, or maybe you are have these are the non-pharmaceutical intervention, or maybe pharmaceutical intervention. You have vaccines introducing, okay, and then you need your vaccination campaign. It will run for how long, and what the efficacy of that vaccination for each group, okay. And then also there is other more advanced, okay, modeling that you model the parameter based on time. Sometimes you switch it on, sometimes you switch it down, sometimes you switch up, and so reduce it. So all this is another optional you can add it, and once you add it and then run it, then you have your model output contain the time and the demography, okay, the value of each compartment that you consider. So that's what epidemic it does. It just break down the process in a standard way and interoperable, make it easy. So separate the model okay, from the intervention, from the epidemiological parameters, and also by default, we are adding a lot of standard epidemiological model built in already, okay, so that you focus more on intervention, don't focus on the well standard SIR model that we are going talking about. Okay, so that's the main message. How we're going to do that in demo, that's what we're going to do. So brief recap again about the SIER model is it's a complementary model. You have the susceptible and then become exposed by rate of by force of infection, and then they can, after that, they spend a lot of time or some time to become infectious, and then they recover. The recover here is remove actually whether you die or just or just recovered and alive. So it is recovered, okay. And it's used to study, and we have vaccination also. If you have vaccines, and you have vaccination campaign, and then we have parameters that move. Those are the rates that move the individual from one compartment to another. And so some of them, for example, the onset of infectiousness, this is maybe the incubation period or latent period, depending on the disease that we are talking about. This parameter is intrinsic about the disease. This is more or less we can identify using clinical trial and contact tracing. This can be identified and will not be varied. We know what the probability distribution of that parameter. And recovery also, how long it takes in average to recover from certain disease. This is also from historical parameters we can pull out from every parameter. From others, this will be known. So, and V sometimes is not exist for some diseases, and B, the beta here, the force of infection, is actually, that's what, make it vary from a society to society, because this depends on our social and economic behavior, how we are interacting, and the structure of our community. And that's a bit hard to determine, but in mass, we know that beta is a link to the reproduction number, which is R naught. If we are in the early phase of the exponential phase of the outbreak or epidemic, is R naught, and beta is R naught times gamma. So the trick here, which I want to, it also allow us to provide a link between applied outbreak analytics and the conventional, traditional way of doing this mathematical modeling, is this beta bridging us to with the R. We can use the cases, to estimate in a real time this R, and then use that R to approximate or compute beta, and then we run our simulation. So that's the missing link, between the practical and the theory of mathematical modeling, which I want to highlight it. So that's that's the structure, and the epidemic now separate. So our compartment will maybe with this is what we call it model, default, and and parameters are the parameters, and then we can create interventions. When it comes to interventions, so we more or less we cannot say anything about alpha, because this is intrinsic about the disease, how in average. So this is, we cannot say anything. For the recovery also, more or less, if we have a treatment, and then we can, we can accelerate but more or less in mass, we have a little say about the recovery here. It will take it full course to recover, 7 days for flu or 5 days in average. But this news, the vaccination rate, we can control it. We can increase it, can decrease it. This can be an intervention. And the force of infection also, this how the infection happen. Maybe I impose closures, shutdowns. Then we break down, because this is coming. It's actually, it can be decomposed into at least 3 individual parameters. So one of it is a contact. So you can reduce it. Then it's another or you can impose mask, okay, something that you don't reduce the mask, but do something that pharmaceutically reducing down the transmission rate. So that will be the reduction of the transmission rate. So that's what the three main interventions: vaccination, which is pharmaceutically clear, and we also have the reduction of contact and the reduction of the transmission rate. That's a three which is covered by epidemic. Uh, as I alluded before here, the link between this force of infection beta and the R naught. Gamma is the average recovery rate. Okay, we can get it from the literature. Okay, or do some follow some, okay, some people, okay, the in a longitudinal way, some, and then we can decide what distribution that will take. Where we get the R, we get it from incident data from the daily cumulative or weekly cumulative, that in an early phase, maybe in a first 3 week, or how many people we get it. We can estimate R. So here I call it RRT. Some people call it effective R, but depend on time. Okay, so it has a effective reproduction number or basic reproduction, depend on the timing and the size of the susceptible population. But in general, let's say this is a measure for the transmissibility of a disease. So is it number between 0 and negative, positive infinity is a big number, and the bigger the number, the more transmissible the disease is, of course. And so is it, the definition is the average number of new infections that caused by a single infection. So if we want the literal interpretation, then the number of RT at time R at time t is equal in the new infections that occurred in the day t or time t over the all infections before time t. But not all those previous infections are equal in their infectiousness status. Okay, people who infected like weeks ago, now their viral load has been decreased, or they are yet also to be in a good state to 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 transmit the infection. So because of that, things need to be accounted for, because in epidemiology, or what we see from today is a result of past, okay, not the current. If you want to account for, if you want to do real analysis, you account for delays happening. Okay, so that delay is account for here, as you see in the denominator here, all the previous infection we multiplied by a factor called W of t minus s. This is a probability of being infectious after or after s days from being infectious. This depend, okay, S run from 1 to t minus 1, and this the whole operation here. This is a convolution, okay, operator. So we multiply the previous infection by their state of, or weight them by the probability of causing new infection, and the whole this equation called renewal equations, and so that's how you can get your t. Okay, this is well known. Okay, and so in this demo example, we have, okay, let's say we have just four days before incidence for 4 days. Okay, and then we want to compute the RT at day 5. Okay, what we do then, we just run this equation in a backward way. Okay, what we have it at number of infection at day 4, we just have 4 infections, we multiply them by what, because now we are day 4, they have only 1 day of being infected, so we multiply them by the probability of being ability to transmit or cause new infection after just being infected 1 day, so we get a number, and we do the same for the 4 days. Okay, and that's what we get is, okay, that's the denominator. And because in day 5 I have some observation, let's say if we have 10 incidents, then our RT is becoming it will be a okay 2.08. So that's how you easily get your and also correctly and robustly your estimate for RT, which we're gonna use it to estimate the beta and then use that beta to run the uh, mathematical model. Okay, and then we add interventions and see how the trajectory would look like. So those are the two basic theoretical part. I just want to recap with you. Nothing is new. Okay, just a description of the SIR model and then the description of this renewal equation. Okay, and how we're gonna do that in a simple demo. We're going to do it after 5 minutes. So is there? I think Andree, we if you have question, I think we have a last 20 minutes we decide for question. So now I think it's a time for break. We take 5 minutes. We come out. Okay, for according to your time, like after 5 minutes from now, I don't want to say this is the exact time based on my time zone.
Okay, I mean, thank you so much, Andree and Dr. Degoot. So everybody, in 5 minutes time, we'll be back to do the demo sessions, I believe. Thank you so much. So you want to maybe stretch your legs and catch your breath and get ready for the next. Thank you.
Hello.
Hello, Degoot.
Hello.
Okay. Hello.
Yeah, I think everybody's set. Can you show a sign if you're ready, everybody? Good, good. Okay.
Degoot, can you increase a little bit the size of the font?
The size of the phone. Okay.
Mhm.
How is it now?
Oh no,
Was
now
this
it's
too
much.
much?
Yeah,
Yeah. Okay. How is this one?
yeah, I think that's fine.
Okay, that's fine. Okay, so welcome back again. So now let's do quick demo of demonstrating of this scenario modeling user packaging. So I hope you guys have access to the opposite cloud server, because we know that you wouldn't face any package problem in that server. Or otherwise, if you are like me and have the correct package version and install them properly, you can do it. So just follow with me what I am doing. I try to explain every step and as much as I can. And also, if you have a question inline, you can ask in the chat, and Andree is here to help me also to address your question. Okay, so what I am going to do, I am going to open a R file. Okay, let's open an R Studio file using R Studio, and then I just save it in whatever directory I have it. Let's say okay, B Black Mass Association demo. Just we give it a name, and then first thing is in this we need to load some packages, okay, that we need uh, to, to to work with today. So we're gonna work with, of course, with epidemics, which is something important. I have it in my machine, so it's loaded, and then I'm going to also load a social mixture, okay, another bucket that allow us to access some contact data, and also I am going to uh, 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 okay, library called EPST capital. Yes, that allow us to to estimate the RT in implement the renewal equation in an efficient way. And and then we need a library, another library called Epiparameter to access, okay, some of those parameters, okay, from epidemiological parameters. And then finally, I think I need tidyverse, okay, just this to get the access to some tidyverse functionality to handle and manipulate the plots. And so the tidyverse is a suite of packages, including the GE plot. So that's the package that we need to, okay, let me run it. So, and I think successfully we have compiled, okay. And Ferris, we successfully okay, browse those packages into. I need to load data, okay. I need incident data, that the weekly or daily cases of. So we are going to simulate SEIRV model. This model can be used to simulate many directly transmitted diseases that does not require vector or third party. That's mostly flu type. So let's say we assume we want to simulate, okay, an outbreak of a certain type of flu-like disease in a certain African country. So just let load. So we need our weekly incident. In this case, we uh, this we don't have, we can simulate data, but let us use some data that come uh, with this bucket, the APS bucket. Okay, it came with some kind of exemplary data, so we can use it. So that's how we load. Okay, when we load it, we have our data. But let also take these are like, let's take it's a full data set, but let's take a few of them. We use those just to estimate our RT. So let's say early flu, I call it something early flu, okay, data is. So how we access it, because since we have now this access, so we it has like, okay, it's a full data set. It has three object. It's the serial interval data. I will talk about the serial interval and the distribution, but let's take just the incident. And also it's a, I want to filter. I don't want the whole, okay, I don't want the whole data set. So if we just look at this, maybe let me run this down. So incident data, it just contain two columns, date and I. I is the number of infectious. Okay, it varies. Some days we have two, so that's all. But I want to take for the date that maybe just for early phase. Just assume that we have like 2 weeks from now. So from I can take we can filter it. Okay, that I am using this notation is a package, and then I want to access the methods, okay, or the functions. I want to filter for date where is less than or equal, okay, less than or equal to, say, it's, I know this day is 2009, just any arbitrary days. I just want to, to take the early part in May, the 10th. Okay, so this, let's say this is our early flu data. I can run it, and if I view it, we just take the first 2 weeks. Okay, where we see things are increasing every day. Okay, good. So this is our incident data. I want to use this to get a RT. But RT, as you can, we need the probability distribution that give us the status of each infection base of each day. So that means it's actually the generation probability. There's a probability, the correct distribution should be a generation probability. The generation time distribution, where time you spend between being infected and until the period that allows between being infected until the time that you start infecting the others. So this, okay, you get infected, you pass your incubation period, then you develop and your symptoms on becoming infectious and infecting others. That's the generation time, which define the WS that we use it to weight all the infections by day. But that is not observable because it's very hard to pinpoint, okay, to pinpoint the time that you get infected. Okay, you might get infective in passive way, and then later you develop a symptom. But I can pinpoint the time that you start developing symptoms. When you come to hospital, we ask you, okay, when do you start having the signs? So we can pinpoint. And through contact tracing data, also I can identify the time of the symptom onset between the primary case, which he gave, okay, infection, to a secondary case. So the start of the symptom onset between the primary and the secondary, this time called serial interval, then we can use that, okay, as a proxy for generation time, because generation time is unobservable, okay, but the serial interval is observable. So because of that, we're going to use the serial interval, and this serial interval for flu, people hard did it, and okay, people documented a lot in literature. We have several control study of contact tracing data, and we have it. So we can use those parameters. Where we find those parameters, we find them in epi parameters. So let's say we're gonna have the flu, okay, SI from epi parameter. That's why we epi parameter. That's why we, okay, is a bucket, and then it has a database. So epi parameter database. In it, we should identify which disease we are looking for. We are looking for our disease is influenza. Okay, and what epiname? What it has a lot of what epiname we are looking for? We are looking for a serial. Oh, okay, serial, serial, serial interval or interval. Okay, and also there is something called single parameter equal true, because in this database that we are looking for a equal true, because in this database of every parameter you might find a different studies, okay, of assessing or that try, they did a study about serial interval for influenza diseases, and but we won't select the best one. That means that the single parameter means this is the study that highest number, okay, by and large, okay, the study that has the highest number of participants, okay, that's what it does. So you can also, we can actually speak, okay, speak a lot about every parameter, but now for our objective here, we just want to get those information, and it contains, of course, information for different diseases, for different epidemiological parameters. So let's see what this flu. So this flu SI is telling us is this is a bringing parameters from studies that done by these authors, okay, in this year, and then it take, so it's a gamma distribution, okay, with the shape, and then I can flu from, because it has a lot of information, what the perception, what the probability distribution we are using. It just a gamma distribution, this side, and this is the shape, and this is the scale. Okay, so that's the fair. Now this, because this object of every parameter contain all the information, but we want the serial, we need to get the distribution itself. So for that, I need to discretize. I need this flu, okay, SI, make it a discrete, okay, make it a discrete from every parameter there is, okay. First I need to discretize it, and then I need to, okay, convert it to density, okay, density, and a density. I want to compute the density at sequence of, let's say we just wanted a sample 25, okay, a variable from this from 0 until 25, okay. This gives us like the W, okay, and we can plot this and see, plot the our distributions and see, and okay, that's how it look like. Maybe high in the beginning, and then around 5 days, that's what you okay, that the average, okay, time maybe need to transmit from one generation to another generation, and yeah, your ability is high around 5, and then it gets, as the time go on, your probability of being infectious is waning and drastically. So that's the S we are looking for. So once we get, and this why discretization, it help us to the sum of all these probability should be 1. So having all those information, because in order to compute RT, now I think we can compute our RT, okay, because we have all the information. We have our probability of being infectious, and we have this the incidence. So I can say, if from Epi-Estim, okay, we say estimate. There is estimate R. In this estimate R, you need to provide your incident data, which is we call it early, early flu data. And so, and we are going to use a non-parametric. It has a multiple choices, but let's use a non-parametric. Okay, non-parametric. Okay, serial interval, small si. Okay, and then we need to. It has a here where you config and tell the okay, make config. I need to pass my WSJ probability that a list of okay they are equal a SDI that we just compute. You need to pass the W with the probability distribution for the serial interval. Okay, so let's run it. Yeah, I think we successfully run it, and actually you can plot. The good thing is here you can plot and see. Okay, let's plot the RT output. I call it the output slash RTS. Okay, and run it. When we run it, you see this is how it look like, the three information that we pass. Okay. Okay, we have a curve of incidence. It look like this, and then this is a estimate how our RT look like over time, and this is the probability distribution that we use to okay to account for the delay of being infectious. So that covers the first part, okay, about the RT. Now I want to quickly to move to the second part. But in this second part also, because here we have like distribution of RT changing over time. So let's just take our mean. Okay. So I'm going to take the mean of like output of RT. RT itself is also contained. Okay. R, and that R also is actually so it's nested objects. Okay, because it has a incidence curve, it has a distribution, and then this R, and these are also every time, as you see, at every time point we have the lower value and upper value, and the blue is the mean one. But I am taking the mean of the mean one to be my my RT that I want to use it to simulate. So this is the first part. Okay, the second part, and of course this I think this code I am writing and typing, but in the POSIT you have access to it. I am just explaining each step how it goes. I might be my naming of variables and things is not typical as yours, but the result will be the same. Okay, so now I need to run the model. Okay, let's run SIRV model on a population, okay, structured way. So then if it's a population, you need contact data. Okay, how the young and old, or how the group, okay, is interacting. Those information come from a social studies. So those information come from social studies, and there is a package. Okay, there is a package called social mixer. Social mixer is just how to it contain surveys, and then from surveys that the people ask question about your diary, plan and how many young you want. So you get a lot of data of behavior. So like let's list surveys. So it comes with a lot of surveys. It might take a time. okay for you, but for me, but for you, I think already loaded in the server. I don't know about you. So it contains a lot of lists, and this is also you will notice that okay, a few African country has been done such a kind of social studies. One of which is Zimbabwe, Gambia, I think South Africa, and Zambia. Or so others you can use information to extrapolate. Okay, if we went to compare for Uganda or for Rwanda, there's a bucket called contact data, which you use, the information of just the number of young people and the number of population in this country. They used to extrapolate, which is not correct. Okay, so anyway, it's taking a bit of time to connect. Okay, because it's require a lot of time, but I know the link. So let's get Zimbabwe survey. So from social mixture, I think we're gonna ask for social mixture get survey, good, and then all what we need, we pass the survey link. So the survey that contains the information is I want to show you actually why I am doing that. Let me stop it. It might take time, though, but I know the link we have access to check is in the Zenodo repository where you contain. So I want to download that survey here down. So that's what we are saying, and why that is became important. It became clear once we have our survey, which will contain contact data. We can extract contact data from the survey. Let's say contact data. Okay, it just I say social mixture, and we are using like a bucket double quotation and then the function just to let you know this must come from what bucket. So I need to identify what country I am looking for. Countries. Okay. Countries, yes, is Zimbabwe. And that you can leave it open or empty, or you cannot. It's optional. Okay, but you need to tell the survey which survey we are looking. We are looking for the Zim survey that we are just downloading. Okay, and here you will tell the age limit. Okay, how many group categories you are looking for. Let's just look for between 0 and this or 50. This 3 age group, people from young, from 0 to 25, 25 to 50, and above 50. This 3 age group that we are looking for. And I say so contact might not be symmetric. That means symmetric equal true. So this means contact can vary between this age group to age group, but there is a way that we can make it symmetric. This is mathematical trick built within the social mixer function. It does for us. So if we run it, is I have problem with loading the yeah. So this is a heavy survey. It's taking some time to load it. From Zenodo, so sometimes the server is the website is down or a lot of access to it. But so start downloading. Good. So getting social contact data for Zimbabwe, download, and good. So assuming that we get the correct survey, then we convert that survey to contact data, which is the main important thing. You pass the survey name and then the age limit and set this symmetric variable to true. So once we get the contact data. Contact data will come with a lot of information. So we're gonna get the contact matrix. Okay, contact matrix is the same here. I will say from this. So a so this is a sequential step. I need to do the Zim survey correctly so that I can get access. So it will come with three objects. One is the contact metric, okay, and the other is a population. Okay, in how many population in each group, and also the proportions. So we're gonna take. I think now we successfully downloaded. Zim server is not available. Is it? Uh, oh, there is an error in downloading again.
Yeah, I think that you can keep trying just to
Okay.
complete a
So once
event.
we yeah. So sorry for this. Okay, inconvenient. But once we just get this contact data, okay, it could have a it come with as I said with three uh with three objects. So it come with matrix of the contact matrix and the population and the proportion of those population. Here, those the contact matrix, the way that it has been defined in a social mixture is different from the way that we use it into epidemiological analysis. So because of that, contact matrix contact defined from group I to group J, but in epidemiology, contact to group I from group J is the opposite way. Because of that, why I am doing the transpose here, converting a row to columns, a column to row, and yeah, and then I need to define my okay demography vectors. Okay, the once we then the demography vector here now is will be I say the demography vector vector is going to be because now the contact data, okay, it will come with demography. Okay, it comes with the demography. It comes with demography object. In that demography object, it comes with population. So I will take the population. Error again in downloading. I don't know, Andre. Shall I change it to any other country or
Yeah, possibly it's because a network issue. Yeah, it can work if
yeah,
you
it's a
change it
network.
to Vietnam.
Huh?
Vietnam should also work. Let me share you the
Okay.
survey
Yeah, yeah.
link,
Give me the okay. Server
or
link for Vietnam.
possibly use the polymod at the end. I mean, as last resource.
Polymote, yeah, Polymote is a service that already attached to social mixture, so we
Yeah,
don't have these internet issues.
yeah.
Uh, I was thinking, yeah, this can be preloaded, but anyway, so let's see. This is my last time, a or let me just stop and use maybe uh, okay,
Polymod Italy.
and just yeah, okay. Italy might be closer. So let's stop this, and then we have a okay. Zim survey is going to be social mixture, uh, social mixture, polymorph. So polymorph is a survey that contains a lot of study in most African European country. So Andre is telling me just change this country to Italy. Okay, let's run this. Uh, yes, let's run this. Okay, good. Now we have it. So this is our contact matrix. Okay, yes. Okay, this is our contact matrix. Okay, we have the three groups, and then this is our demography vectors. It will tell you how many population you have in each okay group. In maybe in Zimbabwe distribution is not like this. This is coming from Italy, most but in Zimbabwe you have more young people as uh, it has. So that's all. We can actually name it. Actually, name also. We can play with this vector demography vector. I want to just give them the same name. It will be equal the raw name of the contacts matrix that we have. Okay. So we have create our demography vectors. And then we need to define the initial values. Okay, let's say we have initially we have one infectious in each million people. That's okay. That's simple assumption, but you can play with. Okay, then we since we get this is the initial I. Okay, you have one infection in each million people. You can play with this. Okay, and then we can create our initial vector. So because now you have three groups. Each group okay has the S and I, and so it's just going to be our S is 1 minus. So all the people susceptible except the infectious ones. So for that why I have the initial I. Okay, these are the proportion of the people. Why I am not getting the initial I correctly? In it. Okay. Actually, this is the. Let me do it correctly. Okay. I should identify the number of the susceptibles. And let's say the exposed, we don't have any exposed. And then also, let's say what about the I? Okay, the infectious. Infectious is the initial I that we have it. Okay. And and then the V, the R, okay, we have no recovery. And then finally the V, we have also 0 vaccinated, then become SEIR model. So the final initial condition should be a matrix, okay? Our final initial condition, so let's say initial, okay, condition should be a matrix because this initial vector represents just one group. Okay, maybe the young. So I need to pass as a matrix. So, and I am assuming that the same initial condition apply for all the three group. So all I need is just pass the initial vector. Okay, 3 times. First represents the first group or first age group, and the second is the second age group, and the last is the last age group. Okay, that's our initial condition of it. Good. And the same way also I can name the raw names. Okay, let's say name the raw names of this initial condition. Just initial conditions is equal going to be the raw names of the contact matrix. Yes, contact matrix. Okay, good. So yeah, this is just for it is not necessary to do this, but let do. So now we have our population. We have all the ingredients to generate a population. So let's say we have this Zimbabwe population or whatever. we need to create the population object. Okay, so this is where now epidemic can come. Epidemic, okay, and then population. Okay, you can give a name for your population. This we call it Zimbabwe. Okay, and we need to pass the demography vector. Okay, you have to identify your demography vector. I think we have it as a demography vector. Okay, and then we need to pass the initial condition as init condition, and also we need to pass the contact matrix. Okay, as a CNT matrix here. Okay, so that's the ingredient we needed. Why we are preparing all those just to pass. Okay, might not, if you are just studying homogeneous, you don't have vectors, but still you have to pass as a vector so that you have one group that is a vector. And all these things also, if your matrix is just going to be matrix of one, matrix of a scalar one. So that's how we define our matrix. Now population, we have it. Now let's say let's say run the base model. Okay, let's say run the base model. The base model is going to be let's say from epidemic, where this base model there is called a default model. Okay, that SEIRV model. So once you pass it, then you need to define your population. Okay, our population in the Zim population that we define. Okay, and we need to define the transmission rate, the beta. Transmission rate, as we said, is going to be RT, which we get it the mean, why we did the the renewal equation and everything, which we get it RT, the mean of those one, over gamma. Gamma is actually times gamma, but gamma is a reciprocal of the recovery. You can come the literature and get the value for it, but now let's assume that in a 1 week, okay, you can recover. So that's our gamma. And then there is a recovery rate is also okay. Okay, I need to add the comma so that I know I am in the right. Recovery rate is 1/7. That's the gamma. Okay, again. And then what the infectiousness rate. This also you can search the literature and find the value, but let's say you are in after every 3 days or so 2 days, you're going to develop, okay, move from being exposed to that's only 2 days. Okay, this is pre-infectious period, like, okay, and now I need to tell, okay, the timing, the interval. We want to run this run model for how long? Okay, the time n, okay, is equal to be, let's say, run it for almost 2 years, okay, or 600 days, and your time increment, I say increment should be like daily. I want to track the model based on a daily basis. So that's our base model. Okay, let's run it. A error in a population compartment initial condition fail must have exactly a Zim population X initial condition must have exactly 5 columns but has 1. So initial conditions is So let me say, it's telling me that some so how this come?
I think you can try to rerun line 58.
Okay. And then let me check my yeah, it was just giving me, yeah, now is correct. Yeah, I just need to rerun it. That's okay. Yeah, good. So again, let me run. Okay, Zoom population, and then yeah, let's run it. So I think we have successfully run it. Okay, now let do plotting and see. Okay. Okay, so we're gonna take the base model, contain all the information and output of the. So let's just filter. Okay, I don't want to get, or let's just filter track the infectious people. Okay, filter compartment equal I. Okay, all the compartments so equal infectious actually. Uh, Infectious. Okay, so this equal or equal, yeah, is equal. That I am just, it has all the compartment, the I and S, just I am focusing on the and then let plot this of per. Okay, and let also why I am writing it in the console is better to write in the file, so that it's also uh, so what we do here, after I want to plot it, so we are going to take GG plot. Okay, I need to, our data is the base model data. After we just filter the contain the infectious, and then I need to specify the aesthetic of the plot. X is going to be, okay, X is going to be time. Okay, because time is also a column in this, so I don't need to tell it. And then the Y going to be a Y value. Okay, because time is the simulation time and value is the value of the compartment, number of infections. And then I can color it by the demography, group. Okay, so that's and then what line I needed, this ggplot sign, I add a layer of the geometry of the plot, then geo line. Okay, and yes, I think what else, I can say S labs. Okay, I can say X was the is the time, or okay, in days, and this is just decorating the graph, and I'm going to, this is this may be number of infected uh, individual. So the rest is decoration. Okay, decorate the graph, give it a certain like here, because that's how it look like. Okay, you can of course let me do my last decoration, which is a plus seam. Okay, plus seam here. Let's get the BW seam. Okay, yeah, black and white seam. I don't like the yellow seam, so we rerun it again. So a simple seam. Okay, so that is how it look like. Okay, that's how it look like in just in these observations. This is how it look like. Okay, of course we can decorate it better, but for sake of time, I am rushing. So this is the bare model. Okay, but the good thing is the model object, once we define it, then we run the model, apply the parameters. Okay, now let's say we define an intervention. Okay, no, we want to close the schools. Okay, we want to close some work or whatever. Okay, let's define intervention. Close. workplace, just a name. We define it in epidemic as uh, intervention object. Okay. The good thing is we're gonna give it a name. Okay. We can say close work. Underscore work. And we should define what type of intervention. Type is contact. When you close work, that means you avoid deny people from gathering together. You're reducing the contact. So this is going to be contact. Okay. Mask might be it's a contact type, and the good thing is the time begin. You want to apply it at what time? Let's say we apply it after 100 days from the onset of the outbreak, and then the time end, and then a time end. Let's say we run it for another 100 days and see. Okay, it's going to be 200, but 100 is just 100 plus 100. That's what we like it. Okay, you want to run it for 100 days, where it start to time that you want to end it, and then we need to define the reduction. Okay, how much is reducing? Because now you pass it also as a matrix. How much is reducing? You close the whole world. Maybe it's affect the young children still they are meeting in the neighborhood, whatever is okay. It have, but for the working people it's okay drastically reduced, and for the elderly people still they have some social event. Okay, so that's what you believe about reduction rate. This is something you come with it. Okay, so also you can access it through social surveys and those kind of. So that's you define our error in contacts. Okay, contacts, not contacts. Okay, that's what's telling me. So here we define our interventions. So the good thing is we define another model too. Now is going to be also epidemic default epidemics default model. So everything I want to be remain as before. Okay, it's going to be Zimbabwe population. Is the same parameter. Okay, everything is going to remain same. At least I want to pass intervention now. Okay, intervention is just going to be list of contact. Contacts equal. That's the thing that we just define it. Close work. Close work. That's all. I think we run this successfully. Yes. So yes. So that's all. We just adding this intervention to the existing model. Okay, let's run it. A successfully run, and then I am going to use the same my bat decoration plot just for the sake of time. Let me just copy it, and all what we need is let's just use model 2 to filter all infections group, and then run it and see how it look like. Okay, so do you see these dips? Okay, which is not, so the effect is very simple. Maybe we have just a little bit of dip, but in order to make it more clear, maybe let's say this has been reduced to like 4, also 2% for the kids, and then we rerun the model. I think interventions. Yes. No, I think I this yeah. Let's run it. Let's reduce to 2% here. Okay, and then run model 2, and then let's plot it. You see, it has a less number now. Okay, you see there is a alter. There is a change in the trajectory here. So, and because of time, I am not having enough minutes to to decorate it better, to annotate better, and to also superimpose the both. Okay, plot the two models in a one figure, so that you see the differences and scale it also down properly to, or zoom it in properly to see the differences. That's how it works. Whatever intervention you have, either the vaccination or reduction of or the reduction of rate parameter, or reduction of a contact parameter. That's how it works. And Epidemic came with a lot of standard libraries for Ebola, for COVID, for of course the SI area model, but for the area also for the for the emergency and settlement, uh, the Fiteria model. But the good thing is also there is an extension. If you know the domain knowledge language, okay, domain specific language like Odin, which you use to describe the mathematical modeling, you can use Odin to write down whatever system you come with and follow some standard trips. Then you can apply use of interventions objects that provided by Epidemic to run it to have a successful simulation. So here I think I want to stop right now. And sorry, it might take more than what I expected, but yeah. So I stop. Yeah, time for questions, and back to Andree, where he can wrap up uh, the presentation.
Should we close with the slides or directly go to the questions, Degoot?
Yeah, I think we can go to slides. Okay, so you want me
Yeah, I think
to
that
share the slide? Okay,
I think that
or
I'm going to
before?
move that. Yeah, I think that I can do the sharing. That's
Okay,
fine.
okay, okay.
Just finalizing loading it. Yeah, just to have a brief wrap up. So yeah, now you should be looking at my whole screen. Yeah, I mean, to wrap up, so thank you very much, Degoot, for the live coding. I've been sharing some links in the chat about the information of each of the packages that Degoot was showcasing. I mean, I think that we explored at least 3 or 4 different packages, and from the good presentation, we followed this one of many paths in this pipeline. Like we imported line list data, we double checked that it was an incidence format, which means a number of new cases per day. We usually, if we have line list data, we need to convert that. We access to the distribution delay of serial interval for influenza, estimated the reproduction number at the exponential phase to approximate the basic reproduction number. And then we try to access to Zimbabwe, but we access to the preloaded in Italy dataset, social contact survey, and demography vector, number of individuals per age group as estimated from surveys. We added the close work intervention and to simulate like a reference baseline model and also an intervention scenario. So yeah, so this is like one way that you can connect different input and outputs to get to walk through all the stages from this outbreak analytics pipeline. Possibly just to close, as you also realize in this live coding, this is a whole ecosystem of R for outbreak analytics and modeling. And we are really interested for you if you learn about all the different tools that we used, because as we mentioned in the chat, for example, we use Epiverse-TRACE, which was a package that was built from previous efforts in the ecosystem. Also, we used a social mixer that is around here. Social mixer is also part of the EpiForecast initiative, and we integrated them with EpiParameter to access to the serial interval. And lastly, we ran Epidemics for the infectious disease model of an SEIRV, and jointly with dplyr and ggplot to make the plot. So we are kind of integrating different pieces from the field and outside the field. Just to finalize, I'm just going to share all the links in the chat after finalizing this, but be aware that you can follow different paths. You can try out these tools and found how much useful are them in your practice. You can also share them to people that you know that is closer to the like frequent deployments in outbreak analytics, outbreaks in general. You can also try to redirect to some global forums for collaboration. There is a WHO collaboratory. It's an open forum. You can be part of that, let's say, forum. We are part of that, so we're trying to approach all our efforts towards that initiative. You can explore all the different links of the packages that I share with you. And you can also, if you are close to developing a code base, you can also try to inspire from the standards that we followed. And also, as I suggested, you can also help us to contribute, fill in issues, like suggesting what parameters you would like to see. If you would like to see vaccine preventable diseases as parameters to use any of these packages, let us know on issues. You possibly only will need to create a GitHub account and then let us know through discussion forum or issues if you're interested to contribute to any, or contact the maintainers to have any improvement that you find appropriate. Yeah, and I think that we can now open the doors to any question, but this is just to close. Thank you very much for your invitation, for hearing us, for staying with us at the beginning and also during the live coding, and also thank to all the contributors from this initiative that in some way they provided code, comments, discussions, or issues throughout this time. So it's also worth to let them know our appreciation for their contribution throughout this project. So yeah, that's all. Thank you very much, and we are open to any questions you may have.
Thank you so much. I suspect maybe you have addressed this question already, but Oluwafemi Samson Olagbami has this. Is asking if there are resources on model fitting and parameter estimation also. So I don't know if that is what EPS team does or something.
Degoot, I don't know if you want to go there.
Yeah, I can go. So for the parameters, we accept the RT. We use it to estimate, the force of infection. But the rest we rely mostly on a trusted literature. Okay. Available parameters. We don't. Here we just, it's more of like we are not inventing new algorithm. We are just putting in a way that can be accessible, understandable, and quickly by someone like non-pro mathematician. But for mathematical researchers, they can also utilize it in order to, okay, if you want to come with some model and you believe that can explain certain disease better than others, Epidemic give you quick entry to explore the potential of what you are seeking. Okay, so give you a quick way to simulate.
So from the look of things, if someone is interested in adding that layer to it, it's open, right? Like if someone is
Yeah,
interested
it's
in doing
up.
a robust parameter estimation kind of thing. Interesting. Okay.
Yes, yeah, good. So it's all about open. And we are not inventing any new methodology. We just repackaging the existing one, refining them so that become interoperable and
Mm,
also address a certain task in the pipeline of outbreak analysis.
mm. So I think the emphasis is on the outbreak. So for outbreak, we don't have time to look for so many things. We
Yes,
just want to
yeah,
attack the situation like in wartime. Yeah.
yeah, exactly.
Mhm. Right. Okay. Are there any other questions, please? Okay. I mean, it's been a very long day, and I must seriously appreciate our facilitators, Andre and Abdul. Thank you very, very much for your time. We're very grateful. We do not take it for granted. I sus Oh, okay. And thank you for all the plenty links. I'm also documenting them so I can package and share later with our community people. So maybe I will find someone who might be interested in also taking part and maybe contributing something to it one day soon. Okay, so if there are no other questions, on behalf of the Black in Mathematics Association, I thank both of you, our facilitators. Thank you for taking time out to do this. We have learned a lot. I'm sure everybody in attendance has learned a lot. Thank you for what you do for our world, because we are in that phase now where we have to be ready for anything that might come at any point in time. And we really appreciate your contribution. We appreciate your inputs. We hope we'll see somewhere one day soon. Thanks a lot for your time. So, for people who are new to Black in Mathematics Association, we are basically that community of people for people of Africans and people of African descent across the world, wherever they are found. So we are building a community where we collaborate, where we work together to also give our contribution to the world of mathematics. And I mean, we have a lot of people who are biased towards epidemiology, disease outbreaks and things like that, and that's why we're very grateful for this. So we have this quarterly. So interestingly, this is a very nice way to round off our webinars for this year, because this is the last one for the year. So the next one will be sometime maybe January, February, or March for next year. And this is a very noteworthy one. So for people who came later, or I mean, I know this, we have to go over it over and over again to really master the process. Thankfully, we have this video recorded. And I don't think, do you have a problem, Andre and Abdul? Do you have any problem about us putting it on our YouTube channel? Is that okay? Okay, nice. Okay, so we have it there always. So if you need to revisit it, or maybe you didn't really have time to follow, you can always go back to it. And thankfully, we have all the, maybe I'll put all the links and everything in the description so people can actually, so you can actually get very busy with it if you are really interested in it. So and on a final note, I appreciate everyone in attendance. Thankfully, not so many, so I can mention names: Agbo Ene, Amankador, Abindu Balkis, Charles Obiora, Idisi Okay, that's one of our BMA members, Dr. Isaac Lekon, Kwame Charles, Oluwafemi Samson Olagbami, and we have an associate prof here, Rosemary T. Abba. Thank you for being here. So once again, thanks a lot, our facilitators, for your kindness. Thank you for your time. So we'll continue to communicate with you via email. It's been such a nice time interacting with you, and thank you for exposing us to this whole world of Epiverse. I mean, it feels like a universe of many tools, and we are very grateful for that. So on behalf of BMA, we are very grateful, and we'll be in touch as much as possible. Thank you so much. On this note, we can end. Do have a great time, everybody. In Japan, it's already 12:36 a.m., so it's Friday already. So anywhere you are in the world, do have a great time. I know Dr. Degoot is in Kigali, Rwanda. It's still daytime, and of course, Andre. I don't know. I feel like calling you doctor every time. Like, yeah, I don't know if you're working towards that, but it's fine. So have a great time in London. Everybody, thank you so much for attending. Bye. Thank you.
Bye bye. Thank you.
Yeah. Bye.
Thank you.